Hello, guys. Good afternoon. This is the teacher Miguel again. And for this lesson, we are going to work in the physics subject, and we are going to work in your physics book. And the topic for this lesson is the modeling the solar system. So let's start. We are going to check the vocabulary that we are going to use in this reading part. We are going to work in this book, and we have here gaseous is a consists of gas. We have orbit, that is the curve, the part of one of object around the another, such as the planet around the sun and the moon around the earth, or a satellite around the earth, and the orbit to move in orbit around something. And we have rocky, that consisting of solid rock. So let's start with the comparing atoms with the solar system, and the objective is construct a scale model of the solar system, but we will not to doing that. We will not to do um, a scale of the solar system. We only going to work on this. So let's start. We have the key concepts, and we have the solar system consists of the sun and the eight planet, as you know, that orbit around it, and the planets constantly orbit the sun and also rotate on their own axis. And there are similarity there are similarities between the models of the solar system and the historical model of the atoms. So we have here a picture of the solar system, and is the sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. So we have here, have you ever seen a scale model of an airplane? A scale model is a accurate physical representation of an object. It maintains the most important aspects, and it's usually just a different size. Scale models help us visualize something that is difficult to see or understand. Scientists often use scale models to represent objects or phenomena that are too large or too small to study easily in the real world. The scales help scientists to communicate their ideas and understand the process and make predictions about the natural world. Our solar system is made up of the sun, the eight planets, and many smaller bodies that orbit the sun. The sun is the largest body and is found in the center of the solar system. If you recall, the gravity is an attractive action at a distance for between object, and sun's gravity holds the planet and other bodies in elliptical, that is oval, that is the orbit, and around it. In other form, the sun, the planets are Mercury, Venus, Earth, Mars, and Jupiter, and Saturn, Uranus, and Neptune. The planets also rotate as they orbit the sun. The scientists divided the planets in two groups based on the size and composition. The the Terrestrial planet, sorry, the terrestrial planets are small, so rocky and relatively close to the sun. They include Mercury, the smallest planets, Venus, Earth, the only planet that has life, and Mars. The gas gigants are huge, made of lighter gaseous and elements, and are far from the sun. So they included the Jupiter and the largest planet, the largest planet, Saturn, Uranus, and Neptune. These gas giants have rings and systems and many moons. The solar system is mostly empty space. The distance within the solar system are measured in astronomical units. That is a U. One astronomical unit is equal to 100 millions, and that is 100 million kilometers, which is the average distance from the Earth to the Sun. In the last topic, we saw the historical models of the atoms and represented with a tiny dense core or a nucleus and surrounded by electrons. So in these and outdated models, electrons and orbit these central nuclear like planets and orbit the sun. Later models improve on this picture of the atoms, and electrons do not occupy an exit orbit, but are found in energy levels or shells around the nucleus. The electromagnetic force, another an action at a distance force, and holds the electrons in place. Now, guys, to get uh, more understand this topic, let's to watch a video with all the information. It's the modeling system.
Hello, I'm Robert Krampf. This time we're going to build a scale model of the solar system. Scientists frequently use scale models to help them visualize things that are too small or too big to really see. For example, you may have taken some modeling clay and toothpicks and made a model of a water molecule. Now, this is not what a water molecule actually looks like, but it does give us an idea that the oxygen atom is bigger than the smaller hydrogen atoms, and that the hydrogen atoms are at a 105-degree angle, putting them closer to one end of the molecule than the other. That explains a lot about the behavior of water. So we can use scale models for small things, but we also use them for large things. A good example of that is a globe of the Earth. A flat map just does not represent the Earth in the same way that a globe does. And for it to be a scale model, it needs to have a scale. And for this globe, our scale is right here. Tells us that 1 unit equals 41,800,000 units. That means 1 centimeter is the same as 418 kilometers. So if we measure something on here that is 1 centimeter long, in real life, it's 418 kilometers long. So a scale model can help us visualize things. Well, we're going to make a scale model of the solar system, and that's something that's very, very big and very hard to visualize. And the first step we need is to determine a scale. Now, our scale is based on a very popular way of doing this by using a roll of bathroom tissue. And it uses a scale that each sheet equals 30 million kilometers. And since each sheet is 10 centimeters long, that gives us a scale of 1 centimeter equals 3 million kilometers. Well, this is a fun way to do it, but it tends to get tangled or to break. It blows around in the wind. I have a lot of trouble with the wind here. So instead of using bathroom tissue, we're going to use string. It's much stronger, much less likely to blow around. And we're going to start by taking that piece of string and tying it to a little metal ring. It's the type of a ring that you put your keys on. Use a nice square knot so it'll be well attached. And that ring is going to act as a pivot. We'll drive a stake in the ground to be the sun. We'll put the ring over that, and then we can move to the different directions for different planets and use that for measurements. Once we've got that, then we're ready to measure the distance to our planets. And I've got a sheet printed out that has the scale at the top, and then for each planet it's got the actual distance, the scale distance from the sun in centimeters, and the scale distance in inches. And so we're going to start with Mercury, our first planet, and that is 19 centimeters. And we'll start right here with the sun, and we'll measure out 19 centimeters. And we're going to mark that one in black. Get a nice mark there all the way around the string so it's easy to see. And then I'll make a black spot beside Mercury, and that'll help me remember what color each planet is. For our next planet, Venus, we're going to use yellow, and that is 36 centimeters. So we will start here at our sun again. We will measure out 36 centimeters, and then make a nice yellow spot for Venus. And once again, we'll put a yellow spot there to help me remember. Next is Earth, and we will use green for that one. Earth is 49.8 centimeters. Almost 50. So we'll mark that one here. Dark green. There. And then Mars is 75.9 centimeters. Right there. Then we'll use red for Mars, the red planet. And then we'll make a red spot on our scale sheet. Now those are the inner planets. They're the ones that are close to the sun. They're fairly small. They're rocky. Outer planets are much bigger, they're much more gaseous, and they're a lot further away. So to go from Mars to Jupiter, we've got to go quite a ways out. We're going to go out a total of 2.59 meters. So that's 2 meters, and then 59 centimeters. Now for Jupiter, we're going to use orange. So I'll make a nice orange spot here. And an orange spot there. Now from Jupiter out to Saturn, Saturn is going to be 4.75 meters from the sun. That means we need to add 2.16 meters. So we start here, and we're going to go out 1 meter. 2 meters, and then another 16 centimeters, and then for Saturn, we use pink. Put a pink spot there. Next is Uranus. For Uranus, we're going out a total of 9.56 meters from the sun. That means we need to add 4.81 meters. So we're going to go 1, 2, 3, 4, and then 81 centimeters. And that brings us out to Uranus. And Uranus is going to be a light green. There. And then for Neptune, we're going to go out to a total of 15 meters. That's going to be 5.44 additional meters. So we will do 1, 2, 3, 4, 5, and then 44 centimeters. For Neptune, we'll use blue. And then make a blue mark on my scale sheet. Now, you can include other objects in the solar system as well. For example, you may want to include Pluto, even though it's no longer classified as a planet. Pluto is very unusual. First off, it's very small for being that far out, and it's got a very eccentric orbit. So sometimes it's closer than Neptune, sometimes it's a lot further away than Neptune. So you'll need to check online and see how far away it is on the day that you're doing this if you want to include it. Today, Pluto is just a little bit further, so on our scale it's going to be another 9, so another 9 centimeters out, so not very far. And we'll put a black mark there for Pluto. Once you've got this marked, then you can roll it back up, and then we will take this outside and do our measurements. Okay, well, once you're outside, you're going to need a large area. And luckily, I have a very large area to work with. You want to pick a point close to the middle of your area. And then I've got a piece of metal stake that we're going to use for our sun. I want to drive it in enough to be fairly stable. And then the next thing we want to add to it is a chart with the positions of the planets. Now, it doesn't show how far out they are, but it shows which direction I need to measure for each planet. And we will put that down over our stake, and then I've got some rocks to weight the corners down. It doesn't blow around too much. The next thing we need to add is our string, which is on that keychain ring, which will make a nice pivot, letting the string move freely on our post. And then I've got a piece of a pool float that I cut off to put over there just to make it more visible so we can see where the sun is. So now we're ready to start measuring. We're going to start with Mercury, which is our first dot. Remember, that's the black dot. And so we want to look here to find Mercury. Take our black dot for Mercury, line it up with that line, and that is where we will put the flag that marks the position of Mercury. Then we come out to Venus, and Venus is around on this side, to the yellow mark, following the line out, and we will put the flag for Venus. Next is the Earth. So we will come out, we get to the green marker, and we will place the Earth flag there. Next is Mars, which is out at the red mark. And Mars is around this side, so we need to move around over here. Mars is right there. And that gives us our inner planets, all fairly close to the sun. We can see that right now the Earth is closest to Venus, but at other times of the year, as the planets move in their orbits, the Earth may be closer to Mercury or maybe closer to Mars. If Mars was at this point in its orbit, it would be fairly close to the Earth. Since it is currently here, it's a lot further away. So now we need to move out to the outer planets. And next is Jupiter. So I line my string up with the Jupiter line and come out until I reach the orange spot. And that's the position of Jupiter. After Jupiter comes Saturn. And Saturn is the pink spot, and it is out in this direction. After Saturn is Uranus. And then comes Neptune. And if we want to add Pluto, we go that way. Once we get things laid out this way, we can see that it's very, very different from the picture that you get if you just use a single line with all the planets lined up. That's just not realistic. At different times, the planets are in different positions in their orbit relative to each other. Now, the last thing we need for our scale model is the scale for the planets and the sun. How big should the sun be for this model? The size of the globe? The size of a tennis ball? No. For this size model, the sun should be 5 millimeters, the size of that little tiny round magnet. So if that's how small the sun is, imagine how tiny the planets would be on this scale. Well, to imagine that, Jupiter, the largest planet, would be smaller than the inside of a lowercase o from your textbook. The next planet, Saturn, that's the next largest, would be about the size of a period in your textbook. Uranus and Neptune are both about the same diameter as a beard hair from my beard, so about that big around. And the rest of the planets would be microscopic. You'd have to have a microscope to see them. So you've got a huge area of space with these tiny little planets scattered through it. If you wanted to expand this model to include the nearest star, Alpha Centauri, then you'd have to have 145 kilometers of string. That's 90 miles. So you'd have to go that way 145 kilometers to put the point for the next little star. And that's just the closest. So the universe is filled with these vast stretches of empty space with these tiny little things scattered through them. It's a fun project to try. Because we're using string, it's very easy to reuse it, to redo it. So if you want to try it a month from now and see how the planets have changed their positions, maybe try it every month for a year to see how things change over time. Great way to learn about the solar system. Well, that's all for this time. Have a wonderful week.
Well, guys, this is a small explanation of the scale representations, and we have some exercise in the next page, but I will send you for homework. Okay, thank you very much, guys. I hope to see you in the next class. Thank you and take care. Goodbye.